Let's talk about complex eigenvalues. Find the eigenvalues and the corresponding eigenvectors for a equals -2, -1, 5, 2. We know how to do this. The determinant of a minus lambda I looks like this, and you set it equal to 0. So you're just subtracting lambdas from everything along the main diagonal. Evaluate the determinant, that's what you get. Multiply out the determinant, that's what you get. The two lambdas will cancel, and we have just lambda squared plus 1 equals 0. In other words, lambda squared equals -1, so that lambda equals plus or minus I. It's perfectly legitimate to have an eigenvalue that's a complex number, like plus or minus I. Now let's find the corresponding eigenvectors. You remember how to do that. So again, we start off with this. Plug in lambda equals I. This is what we get, which is really a system of equations. So let's write out the augmented matrix corresponding to that system of equations. We want to get this in reduced row echelon form. So first, let's interchange rows 1 and 2 so that this entry is a 5. It'll be much easier to get it in reduced row echelon form. Multiply row 1 by a 5th, so that this will be 1. This is going to be 2/5 minus 1/5 I, and that'll be 0. So that's what we have. 1.4 minus 0.2i is 0. Next, let's use this 1 to kill off this entry below it. Let's multiply the 1 by 2 plus I. Really, we're going to add 2 plus I times the whole row to row 2. 2 plus I times 1 is just 2 plus I. Then we've got 2 plus I times 0.4 minus 0.2i. Then we've got 2 plus I times 0, which is just plain 0. Add these, and we get 0. When we add these two, we actually get 0 as well. And of course, 0 plus 0 is 0. So this is the system of equations we now have, the augmented matrix. It's in reduced row echelon form. x1 plus 0.4 minus 0.2i, x2 equals 0. Move this stuff onto the other side, and we end up with x1 equals -0.4 plus 0.2i, x2. And since x2 equals x2, this is our solution. So this is going to be our eigenvector, x2 times -0.4 plus 0.2i times 1. Now, if you were to ask Mathematica for the eigenvector, it would give you this, which looks really different. But really, it's also a legitimate answer, because if you multiply this eigenvector by 5, you get this eigenvector. And you can multiply an eigenvector by any non-zero constant, and it's still going to give you an eigenvector. You can multiply it by 5,000. It's still going to give you an eigenvector. So the eigenvector for lambda equals -I would give you this. You could solve it in the same way by hand, or you could use Wolfram Alpha or Mathematica or a TI Inspire to find that. Find a basis for the eigenspace corresponding to each eigenvector. Ooh, eigenspace. What is that? The eigenspace for an eigenvalue is the span of the eigenvectors for the eigenvalue. It's the set of linear combinations of the eigenvectors for that eigenvalue. So let's find a basis for the eigenspace corresponding to each eigenvector. And that's what we end up with. Because we saw that lambda equals I, that was the eigenvector. And lambda equals -I had that as the eigenvector. It's not like we had two linearly independent eigenvectors. We just had one linearly independent eigenvector for each eigenvalue. So that's our basis. It just consists of one vector for each of the eigenvalues. Note that these eigenvectors are complex conjugates of each other. This is a plus. This is a minus. This is not a coincidence. If the real n by n matrix A, and remember, A was a real matrix, didn't have complex entries, they were all real. If the real n by n matrix A has the eigenvalue lambda with eigenvector x, then the complex conjugate lambda bar is also an eigenvalue with eigenvector x bar. So again, this is one eigenvalue, and the complex conjugate, so if we call this one lambda, this one's going to be lambda bar. Okay. What does A equals -2, -1, 5, 2 do to a real vector x? Let's first look at a simpler example. Find the eigenvalues of m equals 3, -4, 4, 3. Also find the scaling factor and the angle of rotation of the linear transformation x to mx. Scaling factor, angle of rotation, you'll see in a moment what that means. Okay, the eigenvalues of the real matrix M equals A, -B, BA. So again, when your matrix is in this form, A negative B, B A, the eigenvalues are going to be A plus or minus BI. If A and B are not both 0, then M can be written in this way. It turns out it's just absolute value of lambda, 0, 0, absolute value of lambda, times this matrix. This is where absolute value of lambda is the scaling factor, and phi is the angle between the positive x-axis and a line segment from the origin to AB. So multiplication by M is really a rotation counterclockwise through an angle of phi, followed by a scaling factor of lambda. Okay, we've seen this, really I should say a scaling factor of absolute value of lambda. Should put those there. Because we've seen this before. That's just rotating at an angle of phi. Okay, so here, lambda equals A plus BI. In other words, it's 3 plus or minus 4i. So M is going to be the absolute value of lambda, 0, 0, absolute value of lambda, times this matrix. Our scaling factor is the absolute value of lambda. Recall how we find the absolute value of complex numbers. The absolute value of 3 plus 4i is the square root of 3 squared plus 4 squared, which is 25, or 5. And phi is the angle between the positive x-axis, which is here, and a line segment from the origin to 3, 4. So phi is going to be this angle here. We can calculate that easily enough. The tangent of theta is going to be 4 over 3 by SOHCAHTOA. So theta is just the inverse tangent of 4/3, 0.9279 radians, or about 53 degrees. Okay, so let x equal 1, 2. Let's calculate mx, because what did I tell you? You'll see in a moment what m does. Mx is going to be 3, negative 4, 4, 3 times 1, 2. In other words, it's negative 5, 10. So what does multiplication by m do to the point 1, 2? Makes it 5 times as far from the origin and rotates it counterclockwise about the origin through an angle of 53 degrees. That's what we meant when we said that the scaling factor was 5 and that angle phi was 53 degrees. Again, here's the original vector, or really that's the point 1, 2, and then here's the transformed vector, negative 5, 10. So again, scaling factor is 5. This vector is 5 times as long as the original vector. It makes our point 5 times as far from the origin, and it also rotates it counterclockwise through an angle of 53 degrees. Does that look like 53 degrees? Yeah, I'd say so. That seems reasonable. Let A be a real 2 by 2 matrix with complex eigenvalues. Lambda equals A plus or minus BI. Here B is not 0. If V is the eigenvector corresponding to lambda equals A minus BI, then A equals PC P inverse, where P is the real part of V, imaginary part of V, and C equals A, negative B, BA. So this is the more general concept. Now here we had to have a special matrix M of this form A, negative B, BA. More generally, this is what happens if we multiply, you'll see in a moment what happens if we multiply x by a vector like this, A. Okay, for the matrix B equals negative 1, negative 5, 4, 7, find an invertible matrix P and a matrix C such that B equals PC P inverse. For Wolfram alpha, the eigenvalues are lambda equals 3 plus or minus 2i, and the eigenvector corresponding to lambda equals 3 minus 2i is negative 2 minus i, 2. Thus, P equals, now you may be lost, okay, P is going to be the real part of that vector, that eigenvector that corresponds to A minus BI. So this is our eigenvector, so the real part of V is going to be negative 2, 2. And the imaginary part of V, this column, looks like this. Okay, it's negative I, 0. Negative I is 0. So in other words, the imaginary part is just negative 1, 0. C, again, is going to be A, negative B, BA. We know what the eigenvalue, that's based on the eigenvalues. Eigenvalues are A plus or minus BI. Since here the eigenvalues are 3 plus or minus 2i, that means A is going to be 3 and B is going to be 2. So C is 3, negative 2, 2, 3. And P inverse, well, if you know what P is, then you can just calculate P inverse on a calculator or Mathematica or whatever. And it does turn out that P inverse equals B. For the matrix A equals negative 2, negative 1, 5, 2, find an invertible matrix P and a matrix C such that A equals P inverse. This is the matrix I talked about earlier. And then we'll have the punchline. You'll see what we're actually doing with all of this. We saw that the eigenvalues are lambda equals plus or minus I, and the eigenvector corresponding to lambda equals negative I is this. Thus, P is going to be the real part of this, which is negative 0.4, 1. And this is going to be the imaginary part of V, which in this case is negative 0.2, 0. C, okay, so in this case, A is 0, and B is 1, because their eigenvalues are 0 plus or minus I. P inverse you can just calculate on a calculator. So it turns out that that's P inverse. And we end up with P inverse equals A. Okay, so now what does A do to a real vector X? What does that matrix do when you multiply it by X? Okay, let's calculate AX, A squared X, A cubed X, and A to the fourth X if X equals, say, 1, 2, and A looks like this. Okay, just grind this out on a calculator or some other way. AX is negative 4, 9. A squared X is negative 1, negative 2. A to the third X is 4, negative 9. And A to the fourth X is back to 1, 2. Very strange. You're back to 1, 2. So what does multiplication by A do to the point 1, 2? Check this out. So this was our original point 1, 2. And then it takes it out to here, negative 4, 9. And then it shifts it to negative 1, negative 2. And then it shifts that point to 4, negative 9. And then we're back to 1, 2. Can you see what's happening? It rotates the point an angle of pi over 2 along an ellipse centered at the origin. If you don't think this is an ellipse, then use some program like GeoGebra to plot the points and generate the ellipse. It's an ellipse, so it's not a circle. It's not rotating this point along a circle. It's rotating this point along an ellipse. Angle of pi over 2 each time. That's why when you do it 4 times, you're back to where you started. Why? Why does this happen? Why does it rotate along an ellipse? A real matrix with complex eigenvalues rotates points along an ellipse. Here's why. We saw a moment ago that if you have a real matrix with complex eigenvalues, you can write it as A equals P inverse. The matrix C rotates the point and possibly scales it. The matrix P is a change of variable. And the new coordinate system is not rectangular. The scale on the x and y axes is not the same. So the path is distorted. It is elliptical and not circular. P inverse then changes it back to the original variable. So that's why A is going to rotate points along the ellipse.